Hello, everyone, and welcome to this talk. I'm Subha Thomas. I'm the developer of the Microcontroller Kit. In this presentation, I'll be going over what's new in 2.0 of this kit and also a little bit on what is planned for the immediate future. So let me start with an overview of the Microcontroller Kit. This is like a 1,000-foot view. In a nutshell, the Microcontroller Kit allows for the automatic generation and deployment of code to microcontrollers from the Wolfram language. And it does that in 3 steps. So first it generates the source code. And then it invokes a compiler and compiles that code. And finally, it invokes a programmer to upload it to the microcontroller. So to use the microcontroller kit, we'll need 3 components. The first is the microcontroller kit itself, which is part of the Wolfram language since version 12. And then it is the compiler and programmer toolchain. For most of the boards that we released new in 2.0, this toolchain is not part of the standard Arduino IDE, but it's a very straightforward and easy process to actually get that toolchain. And I have provided the links for that instructions and in the last slide in case you do not have it. And of course, you need the hardware where we are deploying the code. Now, so in case you do not have the compiler or the hardware, at the very least, you should be able to see the source code using the microcontroller kit. So all this is handled by one function, and that function is microcontroller embed code. And it takes 3 arguments. The first argument is the systems model itself, or the core computation that you want to do on the microcontroller. The second argument has to do with the target. It answers questions like, what is the microcontroller? What are the input channels? What are the output channels? And so on. And the third argument is the mechanism on how you can get that compiled code onto the microcontroller. Okay. So in version 1.0, we added support for 8-bit microcontrollers like the Atmega 328, the Atmega 32U4, and a bunch of Atmega tiny families. And that supported microcontrollers like the Arduino Uno, the Arduino Micro, the Arduino Nano, and so on. And subsequent to that release, we started gathering feedback on what we should prioritize. And based on the external feedback, the Arduino boards came out on top, and that's what we started working on. Yeah, so one of the first things we released in between 1 and 2 was the Atmega 2560, which is the Arduino Mega 25, which is the microcontroller behind the Mega 2560. We released this SAM3 microcontroller family, which, this one is part of version 2, which is behind the Arduino Duo. And the biggest, and we have this one-off microcontroller from TI, but the big chunk of microcontrollers are the SAMD21 and its big brother SAMD51. So this is still an 8-bit, but all the others are 32-bit microcontrollers and are much more powerful. They have more flash and higher speeds than the 8-bit microcontrollers that were part of version 1. So all in all, in version 2.0, we have 36 new boards from various vendors like Adafruit, Arduino, and SparkFun. The workflow, the design is very clean. So the workflow for any of these microcontrollers is the same. So it's going to be very easy to switch from one microcontroller to the other. And all the workflows I show here today will just carry over from one microcontroller to the next. So let me start with a basic example, because first I'm going to load the kit. And in Unix-like operating systems, I can get the serial port to which the microcontroller is connected by looking at the dev directory, dev folder in the root directory. So if I evaluate, right now I don't have my microcontroller connected. So this is the setup. I've now connected it. And so now if I evaluate this, I should see the port to which it was connected. So I take this basic example of blinking an LED. And this is the model that will blink the LED. So this variable X is going to be connected to that port. And if X is a value greater than 0, it will turn it low. And if for any other value, it will turn it high. and it's going to switch at this time interval, and that we get the blinking LED behavior. So if I evaluate that system, and then the second argument is the microcontroller specification, I say what the target is, and the output I've connected to pin 3. So let me evaluate that. And now if so this is also something new in version 2.0, where we have this temporary cell showing what the status of evaluating that function is. And now if I go there, so this LED, I've connected it to pin 3. And so this is just a basic example. So the workflow, as I said, is pretty much the same for all the other basic examples too. So following that same usage of microcontroller embed code, here I still have the output as the third pin, the third digital pin, but the input, I'm going to take a digital input from the fourth pin. My target is still the same, and the core computation is 1. It's just a gain of 1. So whatever input here, I'm going to send it out to the output. So to do that, I'm going to, okay, so I have to, I do not have it, okay. Okay, I'm going to connect this encoder. Okay, so this encoder has 3 wires coming out of it. So let's see it. Yeah, so one is the, can I put it? Yeah. One is the red, which is the positive. Then it's the black, the ground, and the green is the signal wire. So I'm going to connect these. So I'm going to put the red on the positive, black on ground. And I'm going to connect this third lead to pin 4 here. Okay, I got all that right. And now if I evaluate this, and okay, and so this is an optical encoder here. Okay, I have this optical encoder here. Now, as it is seeing this, as it's coming in view and is not coming in view, it's sending a 0 and 1 to pin 1, and that is turning on and off the LED. Okay, here I have analog output. So this one, the reference voltage is 3.3. So if I send half that, it's going to give a PWM signal of 50% duty cycle. So no inputs, just the output is an analog output. So let me go back there. Okay, so now that one, is it uploaded? Yes, so yeah, it's uploaded that code, and now this is at half intensity. If I make it 0, then that should turn it off. Let me see if that uploaded it. Yeah, it uploaded it, and that one should turn off. So yeah. Yeah. So the reference voltage is typically the maximum value that for which it will turn the duty cycle on 100%, but sometimes you may have a value that is different from the reference voltage. And then you can so on all these examples, this is just a shortcut to specify it, but the full specification of any input-output channel is to say what the pin number is, say what type it is, and any other specifications. Here I want the max value 10. If you have no other specifications, you can just say the pin name is of type analog, as I have done here. But here, because I want to give an additional specification, that's why I gave the full usage. I use the full syntax. So now the maximum value is 10. So for 10, it should turn the LED completely on. So let's see. So now once that's uploaded, okay, it's uploaded. Okay, so that's fully bright. Okay, then we have, now over here, again, I have an analog input connected to pin A0, and that unlock output I send out to pin 3. So once that is uploaded, I should be able to adjust the brightness of that LED using the potentiometer I have connected to pin A0. Okay, so this is the potentiometer I have here, and that I've connected to A0 right there. So I'm going to turn this on, and that should slowly make the, so these are like building block examples that you can use for larger applications as well. And finally, I also wanted to show serial in this basic set of examples. So in the Arduino, so here again, I'm taking a serial input and sending it out to the output. And again, the gain is 1. So whatever is coming in the input goes out to the output. Okay, and then on the Arduino 0, the serial input and output that is actually connected to my computer doesn't have a pin output there. So we have to specify that it is the input RX and TX on the programming port. So once that is uploaded, then I can connect any device with a serial input and output, and the microcontroller will be able to talk to it. But here I'm going to use the device framework to send and receive data. So I open a connection to that microcontroller. My script U and Y variables I'm using to store the input and output variables. And then I create a scheduled task object. So if the device is ready, I'm going to append to the output variable what it is reading. And then the data comes in as a start byte, the data, and the end byte. So I terminate at the end byte, and then I'm just going to parse it. Once I read it, I flush the buffer, and then I create an input and send that input back to the microcontroller. So now if I plot the input and output, so it's exactly one on top of the other. So that's why you see the input and output behavior like that. Okay, so now let's move on to external libraries. So for anything that is not in the core code, we have to, for any feature we want to use that is not in the core code, or if you want to use any library from GitHub and so on, there are tons of those. That's where this feature of incorporating the external libraries becomes useful. So because these external libraries are not part of the core, the microcontroller kit needs to know where these libraries are, and that we can give as an optional, that we can give the path to that we can give in this specification in the optional 4th argument. Okay. So once we have done that, to incorporate the code, we also need to know how the microcontroller kit actually generates the code. When in the previous examples, when we were saying that this input is pin 4 digital, it generates code and then puts that in various sections of the final code. There'll be some code to initialize, maybe some code that has to repeat, and so on. So when we're using external libraries, these we give directly. So instead of saying pin name and its specification, we directly say external libraries and in what sections of the code we want to inject these values. Yeah. So I'll also take this opportunity to say that you can inject code like this without tying it to any particular external library. You can just say in the microcontroller specification that you want to add code at this and this location, and it will do it for you. Okay, so one of the things that the Arduino 0 has is an I2C peripheral. So this is the protocol for handling audio data. So what I have here is a microphone from Adafruit, and these are the ground and power lines. And then, yeah, usually there are 3 lines for I2S. So one is the clock line, the other one is the output from the microphone itself, and then the select line, which selects, because it comes as stereo, and it will select when the signal comes. This line will determine whether it's on the left or on the right. So this select we have just not connected. So by default, there's values coming, I believe, only on the left channel. Okay, so let's see how we deploy code to that. So the code I have here, okay, So I'm getting an input. Okay? U is the input here. If I get an input, so if the value is -1 or 0, then I'm just going to ignore that and use the previous value. But if it's not, then I shift it to the right by 14 bits. So this is an approximation, and for my voice, for human voice, this approximation is good. Okay. Yeah, and so this is another option. So now all these variables will be stored as type int. So you can give that option too. So I'm going to do it as an external library. So I say where the library is, and then now I'm going to inject code into various parts of the program. So I say what files to include, how do I initialize it? So I initialize it in this mode with this frequency, and this is the width of the word that's coming in. And then this, because it's an input channel, whatever is read, um, the last argument in loop gets assigned to the input of the core computation. To that. Then in the output, I'm sending it over serial. And again, that's of type int. Yeah, this external byte, I'm still trying to figure out why. It needs that external byte to be 10, not our standard one for it to work. So then I have the microcontroller specification, and now I'm going to deploy that. Okay. So as I said, the data comes in as a start byte, yeah, and then the rest of the data, and this is the function. I just wrote a small function to parse the data. I open the connection to the device, and here I'm not writing anything to the device, I'm just reading from the buffer. And now if you see, yeah, so as I talk, this is the values it is picking up. And so the thing about this result is that it's picking up at every sampling period. Maybe I should just let it run. It's picking up at every sampling period. So it's not really measuring how loud I am because it's missing things. So to address that, what we can do, we have the same model as before, where we shift the input by 14 bits to the right. And then I have this model, which takes a sample of 0 to 127, so 128 values, and then it computes the maximum and minimum of those values. To see this so all the rest of this little code till here, you do not need to deploy code. It's just to show what is happening. I have a bunch of ranges, and this is a utility to create a list of random reals. Now this is if I send this input into that model, okay, yeah, and then if I compute the output response, what it is doing is it's computing the difference between the max and the min. That's the peak to peak of the output signal. So in the first range, 0 to 10, and this is the value for max to min, and so on. So I put this together, and then this is the same as before. I have the header files to include. I start the I2S interface, and then I start reading. All this is the same as before. And then, yeah, so over here, I forgot to mention. The output, yeah. So after 128 samples, it returns the difference between the max and the min. But otherwise, it returns a value of -1, and that's what we see here. It's returning a value of -1, and after 128 samples, it returns the difference between max and min. So I have this post loop code. So if that value is not -1, if the value is -1, it's still computing, so we don't output that. But if it's not, it outputs to serial. And that together makes all that together makes the microcontroller specification, and I'm going to embed that. Okay, so it's uploading. Yeah. Okay, just as before, I have a function to parse the data. I opened, yeah, so the other thing I did here that's different from before is I increased the baud rate, the speed at which it is, because we don't want to miss any of those values. So I set up a scheduled task. So this one is okay, over here. I have two scheduled tasks. This one is a fast task. So this is just getting the values. And I have a second scheduled task, which makes sure that that value doesn't go above a certain value. So this technique you can use. So when you want to get something over serial and then you want to do something else, which is not so time critical, you can set up like a bunch of scheduled tasks. And one is really fast and critical, and that's where it's getting the data, and something else you can do it much slower. Okay, now I submit those tasks. Now it should pick up my sound level. So I'm going to remain silent for a minute, for just for a moment. Okay, I'm going to say hello. Okay, I'm going to try to do it a bit louder. Hello. Yeah, so it's working as we expect. Okay. Okay. So now, so far I had I squared as an input. Now I have some examples where we have I squared as an output. So here there is an amplifier. Okay, I have to first plug this in. Okay, let me get rid of all these. Okay. Yeah, so that's the speaker, and this is that amplifier, and this is that amplifier and DAC connector. And so now I have to connect these pins according to this one. So one wire is okay. So I have to. Okay, let me go back so you see what I'm doing. Okay. So the output of this, the positive, I connected to this switch. So it can get quite noisy. So I have a switch there which I can turn on and off. And the next wire I have, let me bring it in the shot, is the ground wire. The next one over here is the data line, which I connected to pin 9. One is the clock line, which I connect to pin 0. And finally, this one. Okay, let's go back and make sure. Yeah, so again, over here I have a data line, and then there's the clock line, and this one which selects where the left channel is coming in and where the right channel is coming in. And these two pins I leave by default. So the gain is how loud you want the amplification, and this one is for shutdown and how it mixes the left and right channels. By default, it's just averaging those two channels. So let me deploy this code. Oh, okay, so over here, this model here is the model for a sinusoid because it has no damping terms. So if you look at the output response of this, it's two sinusoids. And I'm going to discretize this model. And then I connect it to another model. So this value I chose, okay, which is just the volume based on, if you make it too loud, then it can hurt our ears or can be quite annoying. Okay, and we connect these two and then we put them in series. Okay, so we're going to now do a similar thing. So for this, it has a different library that is supplied by Adafruit. So I say, this is the path to that library. These are the files to include. And I create this I squared as object. 0, 1, 9, and 12 are the pins. We're not really using pin 12, which is data out, but we're using the other three pins. And then we begin this as each word is 32 bits, and this is the frequency, and then I enable transmission. So again, because this is an output, so this int left gets assigned to this first output. Okay, and I put all that code along with that left channel. And then the int right, as the second one, the second output. So because this is the first one, that gets assigned, the second output gets assigned to int right. And once I have left and right, then I can write it out to the device. Okay, and that's the second channel. And this gives the complete microcontroller specification. Okay, so let me deploy that. Oops. I had turned it off, so let me turn the microcontroller back on. Okay, so does it deployed? Yep. So now if I turn this on, you should hear a sinusoid. Okay, let me bring the speaker close to my microphone. I hope you hear that sinusoid. By the way, I think I'm running out of time also. So okay, let me turn that guy off. Okay. So this, I think I'm going to just gloss over the next two slides. So what I wanted to do was use the potentiometer as an input and create a varying sinusoid output. I wanted to adjust the value of the value of the frequency of the sinusoid, and that is this this example. So I'll just leave it here because I don't think I have time to go over that. And the next one, the next example I show is how to deploy code for audio that is based on just bitwise operations. So what I'm showing here, what I have here as the examples in this notebook are just basic building blocks, and we should be able to take them and create much more interesting applications with these. Okay, let me quickly say what's coming in 3.0. So far, okay. So far we have support for a few 8-bit microcontrollers, and now we have support for 32-bit microcontrollers. Okay, so we thought it was a good time to actually polish up some of these internal functions and export and release it. So somebody externally can also add support for various microcontrollers, because as I was developing this, I saw that there are like microcontrollers that are very close. It just needs a little work to get it to get it up and to get it integrated with the microcontroller kit. Okay, so you don't have to like wait for us to like release it. I mean, it should. So these one-off things. So if you want, you can also just develop your own support based off the microcontroller kit. So we're going to add a bunch of functions in this developer context that helps you to add microcontrollers, microcontroller families, and I mean, we support some vendors. You can also add new vendors. So if you look at what the microcontroller kit is using internally for like Arduino Zero, it's using the data for this microcontroller is stored in this variable. Okay. See, so that's how it knows whether the pins you specified is correct and so on. So you can add this yourself now once we expose these symbols. So I assign this to this variable foo, and then I just create my own microcontroller based on that. And now this microcontroller is a new microcontroller, although in this case it's very trivial. It's just a repetition of that. But you can go ahead and add a microcontroller, a new microcontroller or a family like that, and then the microcontroller kit will pick it up and generate code for that. Okay. Okay, so to summarize, The Microcontroller Kit is a tool that enables you to take Wolfram language code and deploy them to microcontrollers. In this version 2.0, we've added support for microcontrollers belonging to SAMD21, SAMD51, and SAM3 families. So you can generate and deploy code using the standard features, external libraries, and also custom symbolic C code. And the coming developer tools provides functionality to add support for new microcontrollers. So this is the link to the Microcontroller Kit itself and various links to set up the tool chains for the boards that we support. Okay, so I think I'll conclude my talk with that. I hope you found this talk helpful. I'm really out of time, so if there are any questions, just send them my way on Pathable. And I hope you find this functionality useful in your projects. Thank you.